Good morning, everybody. My name is Aina Jené, and I work at the European Genome-phenome Archive, known as EGA. I work mainly in the helpdesk team, where we help users to upload data and download data to and from the EGA. And today I will be presenting a short introduction on what is the EGA, what do we do, and I will also explain some of the tools that are connected to the EGA. So, okay, let's start with introduction. What is the EGA? So, as I said before, EGA stands for European Genome-phenome Archive, and we are a resource for permanent and secure archiving of human data. This type of biomolecular data is potentially identifiable alongside phenotypic data. Hence, EGA is a controlled access repository. The data archive at the EGA is provided by research centers and healthcare institutions, and the data requesters are also researchers from other research and healthcare institutions. So if we see this schema, a user requests access and then they are referred to the data access committee, known as that. That will be the ones managing data access requests as data owners. So their request goes through, there are two ways, either it goes through EGA or they have their own credentials, so they can use the DAC tools. And finally, once the researcher has been granted access to the data, they can download these files by creating an account, and then they download the files, being this data normally sequencing data or phenoclinical data. So the type of data will depend for each use case on what the data providers or submitters have deposited to the EGA. So sometimes we will have the sequencing data, sometimes we will have phenoclinical data, and sometimes we will have both. So now we know a little bit what is EGA and how it works, but let me talk to you about the origins. Everything started in the United Kingdom, so it was created by the European Bioinformatics Institute, EBI, back in 2008, and it was an extension of the ENA, which stands for European Nucleotide Archive, and it's basically an open access repository, mainly containing or hosting non-human data at the time, like for now. 5 years later, in 2013, CRG joined, and for today, the EGA it's been co-managed by these two institutions, and our objective is to transform the EGA in the context of Elixir Europe to have a real impact in the development of personalized medicine, and of course, always from CRG with the help of the Barcelona Supercomputing Center. So as for the archive, the EGA volume-wise, we currently have more than 16 petabytes of data archived at the EGA, which translates to almost 4.5 million of files. And for the metadata, we currently have on our webpage released over 3,700 studies linked to more than 8,600 datasets. And all this data is managed by more than 1,800 DACs. And at the moment, our community consists of almost 2,000 submitters and more than 23,000 requesters. So as we can see in this graph, the data has grown over the years, and this data is a mix of small projects from different research groups, but also we contain large-scale biomedical projects such as UK Biobank, also the International Cancer Genome Consortium from Canada, and many others, and more that will come in the future. So These projects, basically at the EGA, we currently are a partner in more than 20 international and national projects. And we are also an Elixir core data resource and a Global Alliance for Genomics and Health, known as GA-4GH, driver projects. So if we separate the projects by different topics, in this graph, we see that disease-wise, we are currently mainly focused on oncology data, where one of our goals is to develop a data model specific for cancer with the help of international clinical partners. However, we're also working on other diseases such as rare diseases, complex diseases, in this case is specific to cardiovascular disease, and also infectious diseases where we're through a pandemic, so we are basically now currently working with COVID-19 data. But again, we're also working in many other scientific topics and infrastructures. So as we can see here, we're working either from going from artificial intelligence to next generation sequencing, but we're also developing infrastructures in discovering, in federation, and in cloud computing. So now that we have a little overview of all the partners and how the EGA works, I would like to walk you through a couple of data reusability stories that are a clear example of the goal of the EGA. So here we have one. In this example, we have an EGA study reference, which is this one, and it's released on our webpage. So at the EGA, we have stored 21 samples from 7 different families with a rare disease called PAMS. So this rare condition is characterized by a complete absence of the nose, and they can also have presence of ocular defects, as we see here. So there was a study that they discovered that this disease is caused by a mutation in a gene called SMCHD1, which has a very prominent role during craniofacial development. So with these relevant findings and the availability of the data being stored at the EGA, it may contribute to design new drugs and prenatal diagnostic tools. And also another example of an upcycling of EGA data is this one. So in here, again, we have 2 different EGA study references. Here's one and there's the other one, both again released and available under control access in our repository. So at 2 different points in time, by 2 different research groups, they deposited data at the EGA related to prostate cancer. And years later, in 2021, this data was downloaded and reused by a 3rd research group that discovered a correlation between the telomere length and several cancer features. So as we see here, this is a great example of the power of sequencing data reuse. So the original researchers, they did study specific genetic mutations and the features of prostate cancer, but they did not focus at all on the telomere length when they were generating the samples. Yet this data was reused and they discovered new features with this data. And lastly, I would like to present you the Federated Ega. So in coordination with Elixir and the GA-4GH, the EGA has established a federated and interoperable network of human data resources that enables the data sharing in Europe, as we can see here. The structure of the EGA Federated of the EGA Federation consists of central EGA. In this case, we have 2 central EGAs, one in Barcelona, in Spain, and the other one in Kingston, Cambridge, UK, sorry. And then we have different nodes around Europe. So each node stores their data locally. So the data don't leave the country or the jurisdiction. However, we have developed a structure that shares metadata in a following the FAIR principles and links the nodes to national clouds, and they are accessed using the Elixir AAI, which is for authentication and authorization. So I am really glad to say that Federated EGA is now a reality, and we have officially launched with 5 federated EGA nodes, which are Norway, Germany, Finland, Sweden, and Spain, and we are looking forward for the second wave of federated nodes. So now I will explain some of the ecosystem of tools at the EGA, and for that, I will present a cycle of EGA data. So this cycle consists of 5 parts, starting from data submission, data curation, data discovery, data access, and data distribution. So for each part, I will present a tool or standard developed by the Global Alliance, so the G4GH, and that is designed to improve the user experience. I'll start with submission. So for submission, we have to keep in mind that sensitive data must be managed very carefully for security reasons. And for that, specifically, we are using Crypt4GH. So Crypt4GH is a file container format that allows genomic data to remain secure throughout their lifetime. So, so from submission to distribution. As we can see in the image in here, so Crypt4GH keeps the data encrypted, and only authorized users can use a unique user-specific private key to access a second key, that it would be here. So this second key, with this second key, you can access the file and use it, and use the genomic data to further analysis. Another standard, and so for data curation, we have this other standard that is phenome packets. Phenome packets is a file format for sharing phenotypic and clinical information. Currently, the scenario currently is that many healthcare systems still rely on manual entries of phenoclinical data, making it difficult to exchange information in a standard way. So with phenome packets, we provide a format of integrating this phenoclinical data in a structured way, facilitating the communication between different hospitals or research institutions by creating an ecosystem of interoperable tools and resources. So the aim of using phenome packets is to enable a whole network of phenotypic data exchange that will improve the understanding, the diagnosis, and the treatment of diseases. And currently at the EGA, via the SolveRD project, we currently have stored, I think that it's over 36,000 samples with phenome packets. So related to data access, we are working with Duo codes. Duo stands for data use ontology, and it uses different codes to semantically tag datasets with restrictions about their data usage. So thanks to these codes, we can provide a shared understanding of the data use intentions. So in this slide, we can see different codes going from NRAES, which is no restriction. This is a code mainly for open access. So for example, it could be used for ENA. And then in here, we have many tags for controlled access. So for example, we have disease specific. It's an example of using data only for medical, well, in this case, because it's hierarchical, so it will be for health, medical, and biomedical research, but only specific to a disease. So let's put as an example, breast cancer. If you take a data set at the EGA with DS and breast cancer, you know that this data can only be used for for the study of the breast cancer, not even any other type of cancer. It's disease specific. So if you are interested in knowing more about dual codes, here is a link of another webinar from VACE, where we explain the essentials of dual codes, and it's publicly available. For data distribution, so at the EGA, we have the EGA Python download client, and this Python client uses HTS-GET. So HTS-GET is a data streaming specification that allows the secure transfer of genomic data. And it has many cool features, but one of them is that it supports range queries, meaning that so let's put an example that we have a BAM file, and this BAM file, it has its own BY file, which is the indexing file of a BAM. So thanks to this indexing file, it allows the download from a gene of interest or any region that you're interested, and instead of downloading the whole BAM file, you download specific regions, which saves a lot of time and disk space. So for that, at EGA, we have some synthetic data sets that I strongly encourage you to contact the helpdesk team. We will grant you access to this synthetic data so you can test it and try to play around with our Python client. And last but not least, during the next presentation, my colleague will walk you through Beacon v2, which is a discovery tool for genomic and phenoclinical data. I think that's the end. Yeah, thank you very much.